Hello, my name is Cody Hansen, and I will be talking about predicting Lyme disease incidence in humans. I originally gave this talk over at University of Iowa, and the research on this project was supervised by Dr. Kate Cowles. I'm going to talk about Lyme disease background information, the data sets we used, the variables we considered, the model we built, our analysis, and conclusions. In our research, we had three primary goals. The first was to predict new U.S. states where Lyme disease would occur. The second was to determine whether the inclusion of data on Lyme disease incidence in dogs improves the predictive ability of statistical models for human Lyme disease incidence. The third was to identify the most significant predictor variables. In order to understand why we built the models the way we did, we must first examine the biology behind the models. Lyme disease is an infectious disease that is spread from animals to humans and is caused by the bacteria Borrelia burgdorferi. It is primarily transmitted by the bite of two different Ixodes tick species. The tick must be feeding for at least 36 hours before the disease can be transmitted. Assuming you didn't remove the tick in time, you would most likely present with the following symptoms. Erythema migraines, or the common bullseye mark that you can see on the right side of the page, occurs in about 70 to 80% of the infected, and it's the most obvious symptom of this disease. Fatigue and fever are also common, headaches, muscle and joint aches, and finally, swollen lymph nodes. If Lyme disease is left untreated, it can present with even more bullseye rashes on your body, Bell's palsy, which is a loss of muscle tone on one or both sides of your face, pain and swelling in large joints such as your knees, hips, and shoulders, and you may have severe headaches and neck stiffness due to spinal inflammation. You may also present with heart palpitations and dizziness. On the right, we have a picture here of somebody affected by Bell's palsy. Why is it important to treat Lyme disease early? Well, in about 10 to 20% of all patients who are cured after acquiring Lyme disease, they will, for their entire lives, have shooting pains in their joints, numbness or tingling in their hands and feet, and problems with short-term memory. The Lyme disease bacterium is primarily spread through the bite of the infected black-legged tick, or the western black-legged tick. This is a range map of the black-legged tick and the western black-legged tick. They prefer high humidity areas, high forested areas, and coastal regions. They are found in areas with plenty of deer and small animals like chipmunks and mice. It used to be rare to find these ticks in Canada or in Mexico, but it seems as though through global warming, their range is expanding. Lower elevations also seem to be important. The life cycle of these ticks typically lasts 2 years, comprising of 4 life stages: egg, larva, nymph, and adult. At every life stage after egg, the tick must feed, which is also known as having a blood meal. These ticks can feed from mammals, birds, reptiles, and amphibians, but primarily parasitize the white-tailed deer as adults. After an egg hatches, the larva begins searching for hosts. At this stage, the tick primarily parasitizes birds or small mammals. Once it finishes its blood meal, it drops off and begins metamorphosis. The next year, the larvae emerge as a nymph where it feeds again. After feeding, it begins its transition into adulthood. Once an adult, the tick feeds and is then able to reproduce. Sometimes they are able to complete another round of feeding, giving them a 2 to 3 year total lifespan. In dogs, it is hard to detect infection because of the hair hiding the ticks. They also do not present the bullseye mark. Testing for Lyme typically occurs alongside heartworm testing, and millions of dogs are routinely tested for Lyme, but humans are not. So the question is, are they our canary in a coal mine? To model fit, we used CDC human Lyme incidence reports from 2007 to 2011 and dog incidence rates from 2011. To test our predictive capabilities of our model, we used CDC human Lyme incidence from 2012 and dog incidence rates from 2012. Our response variable was the total number of new human Lyme disease cases in a given state over a year. Our explanatory or predictor variables were new dog Lyme disease cases reported in that state over a year, the percent of that state that is covered in forest, the percent of that state that is urban areas, morning and afternoon humidities of a given state. Deer harvest is the number of white-tailed deer killed in a given state over a year. And finally, we have the mean elevation of a state and the highest elevation of the state. One useful tool in statistics is the scatterplot matrix. It is a quick visual tool you can use to check for linearity amongst the predictor variables. For instance, you'd prefer to see something like the graph of afternoon humidity versus January temperature, where you cannot really identify any trends very easily. What we don't like to see are graphs like January temperature versus July temperature, where you can see a positive linear slope amongst the variables. If you find linearity amongst your variables, it is typically best to try to remove one of them, as it's typically the case that one of them is not needed. However, sometimes it's best to leave them both, as one may contain some information that the other does not have. For both models, we use Poisson regression due to the response variable, total counts, being non-negative, discrete, and having a large variation in the upper tail of the counts. Because of this fact, using a multiple linear regression model would be inappropriate, as you would not expect the error terms to be normally distributed. Thus, in both models, we link the dependent variable that we assume to be Poisson distributed to the independent variables by taking the natural log of our dependent variable. This changes our dependent variable from a strictly positive discrete dataset into a continuous dataset. Generalized linear models do not take spatial autocorrelation into account, so the significance of every predictor is likely to be overestimated. Hierarchical generalized linear models do contain random effect for each state, which means less predictors will be significant. In essence, the GLM pretends as if the states are in a vacuum and do not affect one another, while the HGLM allows the states to affect each other. And because the GLM does not take state proximity into account, significance of predictor variables is likely to be overestimated. Both of our models are attempting to fit natural log transformed state total counts. Each model has an offset E sub I, which is the expected count if the rate of disease was the same in all states. The phi term in the HGLM is a spatial random effect for each state. Here we have the GLM table of coefficients and p-values. Every predictor variable is significant here. Also, it's important to note that dog incidence is the most significant of our predictor variables because it has the highest z-score out of all of them. Here is the HGLM table of coefficients and p-values. Dog incidence is still the most significant predictor variable. However, only dog incidence, January temperature, and July temperature are significant at an alpha of 0.1. Earlier we saw that in both the GLM and HGLM models, dog Lyme disease incidence was the most significant predictor variable in sample. Here we are attempting to discover which GLM model was best, one that included everything or one that included everything with dogs removed. One way to test which model is better is to compare how far away our predictions are from the actual 2012 data. In the first two, we took the squared difference between the states and found the mean. In the second two, we transformed the data using the natural log and then took the squared difference between the states and found the mean. One criticism of using mean square error to analyze models is that the mean square error is incredibly susceptible to outliers. In the first case, our GLM that includes dogs did a better job than the GLM that did not include dogs. This is due to the fact that on the upper end of the counts, the predicted dog GLM was closer to the 2012 counts. In the second case, the GLM that did not include dogs did a better job than the GLM that did include dogs. I believe this is due to both models over-predicting states with low counts, like Montana, but the dog GLM more over-predicted those low counts. Our study had several limitations. Lyme disease cases are tabulated by state of residence, not by state of exposure. This means if you're from Florida and you were visiting Illinois for the weekend and acquired Lyme disease, Florida would get one count of Lyme disease for that year. Not every case of Lyme disease is reported to the CDC. Only about 30,000 cases a year are reported to the CDC, while the CDC estimates that up to 300,000 cases could be happening in the United States. All the variables are aggregated by state, which means it's very hard to determine individual risk behavior. No new states with Lyme disease incidents were found. Hawaii still doesn't have Lyme disease incidents. And in 2012, the cases were recorded differently. They were recorded in terms of probable and confirmed, and we tested our model against this sum. Conclusions and future work. Our HGLM predictions are much closer than the GLM predictions are to actual values. This means that there may be some variable out there that we cannot quantify, or simply one that we haven't quantified yet. There are some preliminary reports out there that suggest that foxes and possums are negatively correlated with Lyme disease. Foxes eat the white-footed mouse, and possums eat the ticks. Dog incidence rate is the most highly significant predictor variable in both GLM and HGLM models. This suggests that it should be included in future models. And thirdly, we found that January and July temperatures were highly significant predictors. For our future work, we will report our models and answers to the CDC. We will write a paper for submission in an applied statistics journal, and we will be predicting the 2013 incidence rates.